let's look at the questions of fixed cylinders in terms of compound cylinders. The one that I've shared in the group for student 5 at Mateo. Number 9 talks about the steel cylinder with an outside diameter of 260 millimeters. It shrunk onto cylinder with an inside diameter of 180 millimeters and outside diameter of 220 millimeters. So when it comes to this, you have to be careful in terms of those diameters. You see we have a 260 outside diameter. It is steel for both material. We have an outside diameter there which is 260 millimeters. And then onto, meaning that what we have here, we have the one which is the outer diameter of 260. Right, it's a hollow part. It is shrunk onto the other one, which is which one? The other one, which is also the steel cylinder, with the inside diameter of 180 and outer diameter of that. That means the inside, I have inner cylinder, and then I have outer cylinder. Now here I have the diameter, which is 180 millimeters, and which is the inner diameter of the inner cylinder, and then the outer diameter of the inner cylinder, which is also act as a common diameter, is the same as 220 millimeters. Now the weight, they say shrunk, meaning that it's a shrinkage graph. So we need to draw the type of the graph of the shrinkage graph. As we know that we take a system because there's no any pressure being given, so we take it as there's only pressure at the common diameter, and then the outer and the inner diameter for the both cylinders is equal to 0. That means my radial here is 0, and then my radial there is 0. Here we have the internal pressure, which is the radial at common. Then what we say that we are going to have a normal standard graph whereby what we have here, we have that line for that line and that line. That is the lines for the hoof stresses. We have hoof stress maximum for the outer, we have hoof stress minimum for the outer cylinder, right? And then again, what we have here, we are going to have the hoof stress maximum for the inner, and then minimum for the hoof stress minimum for the inner. So that is the maximum, that is the minimum. What we know that here A is positive, and then B is positive, and then A here will be negative, and then B will be negative according to Lenz's law. Now the first question, they want us to calculate the radial stress at a common surface. If the maximum, look here, they say maximum tensile. The top part is compressive, and then bottom part is tensile. So it talks about the maximum tensile in the outer cylinder. That means the hoof stress here is given as 90 megapascal. Then what we say the first question they want us to calculate 9.1. In 9.1 they want us to calculate the radial stress. The radial stress at the common, which is at DC, which is 220 millimeters. The DC is 220 millimeters. What do we know about the formula for that? Radial stress is the same as A minus B over DC squared. So we want to know the constant A and B. Now, because we have given the conditions of the outer, meaning that I'm going to look only at the outer there, cylinder there. Say I have that line whereby here my radial is 0, and then my radial is the one that I'm looking for. And then what we have here for the hoof stress is we have hoof stress, which is 90 maximum, and then we don't have hoof stress minimum. Then if I take a normal box, say that, let's look what I have here. I have must look for the conditions of what I have there. The condition that I have there, it shows that here I have my radial there is 0. I don't have my hoof stress minimum at a diameter of 260, right? But here I don't have the radial in is the one that I'm looking for, right? And then here I have the hoof stress which is 90, clear, at a diameter of 220 because of, like I said, that I'm taking the inner part there. So I'm going to work diagonally there, right? Forget my A and B and don't forget what I've said here, right? And then I'm going to start saying, like I said, consider the inner, not the inner, the outer cylinder at D, which is 260 millimeters. My radial stress is the same as A minus B over D squared, which is the same as 0. That means my A is the same as B over D squared, which is the same as B as our B. Our B, which is unknown, divided by 0.26 squared. And then your answer will give you 14,793B. That will be my equation 1. Then I'll be going inside saying at D, C, which is 220 millimeters. Therefore, my radial stress, my hoof stress, because they give me the hoof stress, my hoof stress is A plus B over DC squared, which is the same as 90, 10 to the power 6. It will be 90 because of its tensile. But knowing that my A here, it is being solved there. So A will be 14,793B plus B divided by, I'm at 220, so it will be 0.22 squared, which will give us 90 10 to the power 6. Then we say we have 14,793B plus 20,166B, which is 90 10 to the power 6. That is, our B will be 90 10 to the power 6 divided by our A divided by the coefficient there. It will give us 14,793 plus 20,166, and then that means our B will give us the value of, let me put it in the right position, our B will be 2,539 10 to the power 6, right? Now, as we have said that our A is the same as, here when we said our A is the same as 14,793B, we can also look for the value of A. That is, our A is the same as 14,793B, which is 14,793 multiplied by our B, which is 2,539 10 to the power 6. That leads us to 37,552 10 to the power 6. Right. Now, then I can relate to saying add DC to the question, which is 220 millimeters. My radial stress is the same as A minus B over DC squared, which is the same as our A. Our A gave us 37,552 10 to the power 6 minus your B, which is 2,539, 10 to the power 6, everything divided by DC, which is the same as 0,22 squared. Therefore, the total for AA for the hoof stress will give you minus 14,909 megapascal. Minus shows compressive, which is 14,909 megapascal watt compressive. Right? So then 9.2. 9.2, it says to us the tensile stresses also calculate the tensile stresses in the inner and the outer diameters for both cylinders. Also draw the stress diagram. This is the stress diagram here. So we are going to draw determine the inner stresses and the outer, for the inner and outer diameters, the tensile stresses, meaning that the hoop stresses. Then what we say that, okay, as I have that, meaning that I still have the line of the outer. For the outer, what I have here, I have the hoof stress maximum, which is given as 90. Now I have my radial there is 0. I have my radial here, which is 14,909. As we notice that is the negative side, that is the positive side. One thing left here is a hoof stress minimum. Then I can say it's at D, which is 260, and here I have D, which is 220. Then I can say that at D, which is 260 millimeters, my hoof stress minimum is A plus B over D squared according to the Lenz's law. My A is 37,552, 10 to the power 6, plus the B, which is the same as 2,539, 10 to the power 6. Everything divided by 0,26 all squared. And then it will give us our hoof stress for minimum as 75,091 megapascal. Right. And then we should also have to look at, are we correct there? So meaning that here when I have 75,091, let's take these two values, say that will it give us internal pressure. Say my radial will be the same as 90 minus 75,091. So, or make it a negative, make it a positive. Clear? Sure. The difference between the two actually can be either one of the two. Must give you that. So we have 90 minus 75,091. Right? That gives 14,909 megapascal. So the difference is that pressure is spreading in both cases. It's increasing in the maximum, in the minimum, it is decreasing. Right. And then we go to outer cylinder, not outer, but inner cylinder. We are going to look for the tensile stresses for inner cylinders. In the inner cylinders, when I draw my sketch there, I'm going to notice that for the inner, I need to check whether I have the diameter there is 180. I have the diameter there, which is 220. Inner and outer diameter of the inner cylinder. Then my line is going in terms of that, whereby I have the radial, which is 14,909, and then I have my hoof stress there. Because of my hoof stress there will be a compressive hoof stress maximum and hoof stress minimum. I need to get those two stresses. Clear? Now, let's put our box and see of the areas that we have. We must have 4 out of 6. What we have here, we have our radial as 14,9. So we have our radial here, which is 0. No, that's not here. It shouldn't be here. It should be at the bottom here, which is my radial here is 14,909. So we are looking for the hoof stress minimum. That is the minimum. We look for the hoof stress maximum. The diameter there is 180 and the diameter there is 220. Then because of I have the bottom part, I'm going to utilize that bottom part to calculate constant A and B so that I can have the top ones, right? Which shows that at D, which is 180 millimeters, my radial stress is the same as A minus B over D squared, which is the same as 0. That is, A is the same as B divided by 0,18 squared, right? So, which is the same as 30,864b. That also my question 1 again. Then I can go from where I have the value. I'm going to say at DC, which is 180 millimeters. My radius there is the same as A minus B over DC squared because of I have this one is the same as minus 14 because of its compressive 909 10 to the power 6. My A is 30,864b minus B divided by the diameter, which is 0,18 squared, is the same as minus 14,909 10 to the power 6. Which is going to lead us there of saying I have 30,864b minus we have 20,661b, which is minus 14,909 10 to the power 6. Therefore, your B is the same as the B will give you minus 14, 1, not 14, 1,461 10 to the power 1,461 10 to the power 6, right? Right. So that is your A will be 30,864 multiplied by minus 1,461 10 to the power 6. That is your A will be minus 45,097 10 to the power 6. So then, like I said, that from the top part, they're showing that your A and B, it must, because of it's the inner, it should be minus A and minus B, so that your stress might be in a negative part, show that compression. Right, if I have that, then I can say that from my line there, it is the minimum is at 220, the maximum is at 18. I can start with either of the two. Say that at D, which is 220 millimeters, my radial stress, my hoof stress is the same as A plus B over DC squared, right? Which is the same minus 45,097 10 to the power 6 plus B. My B is minus 1,461 10 to the power 6 divide by the DC, which is the same as 0,22 squared, right? So that gives us the hoof stress of minus 75, 282 megapascal, which is the same as 75,282 megapascal what? Compressive. Then I can say that at D, which is 180 millimeters, my hoof stress is the same as A plus B over D squared, D in, right, of the inner cylinder. So, which is the same as, what is the value of A? Minus 45,097 10 to the power 6 plus B, which is the same as minus 1,461 10 to the power 6 divide by 0,18 squared. And then the total of the hoof stress will give us minus 90,191 megapascal. Let's look at the difference between those two to see whether it gives us the resultant. The resultant, we can see that minus 90,191 plus 75,282. And then the total there will also give us minus 14, what was there? It was 14,909. 14,909 megapascal. Right. And then now 1.3. It wants the shrinkage allowance at a common surface. If you notice the formula, okay, let's go write down the formula. 9.3. In 9.3, the shrinkage, it says that the change in diameter 2 minus the change in diameter 1. Mostly we are using only different materials. But on the same material, what we say shrinkage is the same as the common diameter. They say at common all over E is the same as hoof stress 2 minus hoof stress 1. Meaning that 0,22 10 to the power minus 3, right? No, not 10 to the power minus 3, it's 0,22. It is already in millimeters, right? 0,22 divide by 210 to the power 9 into hoof stress 2, meaning that here I'm at the common diameter there, which shows that I'm going to look for the hoof stress in and then hoof stress out at DC, which is 220 millimeters. So it is this minus that, right? That is 90 10 minus 10 to the power 6 minus the inner one is the same as minus 75,282. Sorry, 10 to the power 6. Because here we got S minus 75. Here we are giving already S 90. 10 to the power 6. So, which is the same as what we say we have that will give you 0,181 millimeters. Now, you should notice that the Poisson's ratio is not given. That is, V is not given. So it shows that materials are the same. Clear, they didn't give us the V at all. Now what we say that, let's check for instance if the Poisson's ratio of steel, it was 0,3. That is the same as V. So we could have said the changing diameter of the outer, it is D at the common diameter divided by E, right? Multiplied by the hoof stress minus V times RC at common. Hoof stress 2, right? That means we are still at the common diameter there. That means it's the same 0.22 divided by 200 10 to the power 9 into who's stress 2? 90 10 to the power 6 minus 0.3 multiplied by minus 14,909 10 to the power 6. The total there will give you 0.104 millimeters, right? And then the inner diameter, the inner change in diameter is the same as DC over A. We'll have the same conditions there into what? Into roof stress 2 minus roof stress 1 multiplied by V or stress at common. Because we are still at a common diameter. Therefore, we have 0.22 divided by 200 10 to the power 9 into minus 75,282 10 to the power 6 because of inner the minimum, because we consider minimum and maximum on that line. As we say that we consider hoof stress minimum in, and then more, and then at the bottom where we consider hoof stress maximum because they say at the common diameter at DC. So we say minus 0.3 multiplied by minus 14,909 10 to the power 6. Then it will give you minus 0.077 millimeters. So shrinkage will be the change in diameter 2 minus the change in diameter 1, which is 0.104 minus and minus 0.071. That will give us 0.18181 millimeters. Thank you.